Okay, we are now going to talk about something fairly advanced that you're going to see pop up several times when we change coordinates in Calc 3. We look at parameterized curves and the such. So this topic's going to come up a couple more times, and that is how to find the length of a curve. From Algebra 1, you have talked about how to find the length of a line segment using Pythagorean theorem. And we are actually going to use the Pythagorean theorem to define what we mean by the length of a curve, at least the Euclidean length of a curve. I am sitting here with my two children over there listening on the other computer to what? To popular songs that are parodies in Minecraft. So if you hear some strange music or whatever, you know what's happening. I've got here a function that we looked at just in another video in this experience, this basic experience module, 5 sine minus 3, and I've plotted it. And if you want to follow along, then you should pause and plot this too and make sure you can do it. As a matter of fact, you ought to get that function right there, write it down on a piece of paper, and then pause this and go away from this and see if you can define that function as f and plot it from 0 to 2. Okay? Alright, assuming you've done that, welcome back if you did that, and never mind if you didn't. So I want to go on, and actually I should put this, hang on a second. I'm going to put this in, there we go. Now we're in presentation mode and it's easier to click around and such. So how do we find that length? Well, we first approximate it and then we take a limit. And that theme has come up, what, 5, 6, 7 times already? It's going to come up again since Calculus 1, through Calculus 1. So what we're going to do is we'll put uniformly across, at least uniformly with respect to x, points. We'll pick points here. We're breaking up from 0 to 2 into 4 pieces, and we're just going to connect the dots along the curve. Now, if you'll look, if we took the Pythagorean theorem and measured the distances of each of those 4 line segments, we should get something fairly close to the length of the curve. All right, so how would we do that? Well, we would form little right triangles between the points. And we would measure the horizontal line segment, and we would have some type of way of measuring the vertical line segment and use Pythagorean theorem on that. Now, we always, when we uniformly divide across on the x-axis, we call that length delta x, and basically we take the total length of the interval and divide by the number of line segments. So in this case, we'd go from 0 to 2 divided by 4, and so delta x in this case is what? It's a half. Then the height here would be the height from the previous endpoint. So that's f of, let's see, the beginning endpoint here. In this case, a would be 0. And starting off with k be 1, it would be this point right here, because we would add 1 delta x over and subtract the previous a. And actually, that's a mistake right there. That's a plus. Goody goo goo. Come on now. K minus 1 delta x. And then we take this leg and square it and that leg and square it and add them together, and then take the square root and add up all those lengths, and we should get a nice approximation. To demonstrate how to do that, I've divided this up into 16. So n is equal to 16, and so delta x will be 2 minus 0 divided by the 16. And then what I have right here is the sum. Now because I don't have any decimals, I'm going to take this n off for a second. I'll add up those 16 parts. When I do that, look at this mess. And the reason why is because Mathematica, if you don't put any decimals in, it will compute and keep everything exact. It's one of the beautiful things that it does, is it in internal workings will work with the memory and always keep track of everything if you're not using a decimal. However, let's tell it compute that and then give me a decimal for it. So it says, okay, and notice I don't have a semicolon after this, so it's giving me that value first. So right now my delta x is 1/8, and it's saying the value, the approximate length is about 5.99. Now you might be willing to say, oh well, the length is exactly 6. Well, be careful now. So instead of 16, let's divide it by, let's take 100 intervals and see what happens. 6.001115. All right. Let's take, I don't know how long this will take. Let's take 1,000. 6.0013. Not bad. Not bad. But it seems like that 6 may not be the answer. It might be coming awfully close. All right, well, as we take n bigger and bigger, delta x gets smaller and smaller, and that's the limiting game that we know how to play, so we suspect that there's some kind of derivative or integral involved here that if we take a limit, we can actually get a closed form for the length of this. And actually, this is a beautiful example where a derivative and an integral appear at the same time, okay? And I'll explain why. So here, we'll go back to this formula that we got, and I'm going to pull out a delta x squared out of the square root. Well, when it comes out of the square root, it just becomes a delta x. It comes out of this and leaves us a 1. And we'll have to divide by delta x squared, and so we get this quantity here squared. Now, I want you to look at this, and if you have to, I want you to pause the video and ask yourself, boy, does this whole thing, the summation here, look familiar? If I think of this as just some goofy function, some weird function, some function at each point times the width of an interval, adding those up, does that look like something? It should. And the next question I want you to ask is, if we look inside of here, does this look like something? As delta x gets smaller and smaller, does this inside here look like something? And if you can answer those two things, you may be on the path of understanding some of this stuff. Okay? So I'll move on and we'll see what we got here. So I pull this out, I'm taking the limit as delta x goes to 0, which means I'm letting n get bigger and bigger and bigger, so my intervals get smaller and smaller and smaller. And I first want to take a look at this inside here. That inside there is a difference quotient. It's the difference in the y values across here, this way, divided by the difference of the x values. So it's a ratio of this rise over run. This is a derivative at each of these points. It approximates the derivative at each of those points as the points get closer and closer together. So it's just f prime, where I've got xk being each of these points, the kth point along there. All right. So there's where a derivative appears. I don't have an equals here. I'm saying in the limit, it's going to come. It's limiting to the derivative of at each of these points. The derivative becomes a better approximation to that difference quotient at each of those points. Now, what does this look like? Well, as I've got a function times a height times a width. As we let the width become infinitesimally small as we add them up, we're adding up rectangles. We're adding up rectangles with these as the height at each point. And that's an integral. That's an integral. So now we have an integral formula for the length of a curve of a function from a to b. We integrate the square root of 1 plus its derivative squared. How cool is that? How cool is that? So let's go back and compute this. So we had this. Let's see here. Shh. Children. All right. So what do we have here? We're going to integrate f of x. Actually, that's craziness. 1 plus f prime of x squared, comma, and we're going to go x from what? 0 to 2. 0 to 2. All right, there we go. Integrate. It pauses. It gives us something crazy. That is correct, but what we really want is a number. So we'll tell it, please do this numerical. We could either tell it to do the integral numerical, or the fact that it got a closed form so nicely. Instead of telling it in integrate, I'm going to take the n of that, which means it will go ahead and do the exact answer and then give me a numerical value from that. And so the numerical value is approximately 6.0013, which, if you remember, was awfully close to, well, actually, I think that's exactly what we got when we did the numerical with 1,000 intervals. So yeah, it's beautiful stuff. This is the name of the game. You'll see other forms of this when we do parameterized curves and stuff. Hope that helps.